welcome back to the last of the Geolytix series of podcasts. I'm here once again with Blair. We thought we'd sort of top and tail the series of shows and maybe focus back on some of the things we've been talking about. One of the topics that I think we've mentioned on a couple of times, which is really important to AI and what we do, is this idea of foundation models. And I thought it might be a nice idea to start with you, Blair, on that one. Foundation models, what are they? How are they important to us?
Right. So foundation models is a general purpose framework that can solve multiple geospatial problems. So the idea of kind of the clues in the name, they're foundational. They can be used for many different things. They can solve many problems. So they could help you with flood risk. They could help you with predicting crime. They could help you route ambulances. They could help you decide where to open stores, etc., etc. And within AI, there are multiple intelligences. I think we've touched on this before. There's language intelligence, there's visual intelligence, there's musical intelligence, and there's spatial intelligence. And spatial intelligence is rooted in the core concepts of geography, that things interact. Zeroth law. So if you're going to build a geospatial foundational model, it has to be fundamentally spatial. It has to understand structure. So over the last couple of years, there's been 2 or 3 approaches that various researchers, including ourselves, have taken to try and get to understanding what a foundational model is. And Google have obviously produced the PDFM, which we have had a play with under their early access program. So that's good to get a good benchmark of what's going on. So if I explain the approach that seems to have become the default, the standard approach to building a GFM.
Well, maybe just step back a bit. So foundation models, I guess, is really what most people kind of conceptualize using today. You know, we talk about training a model, we build big data centers. They're primarily training to create foundation models in general terms. But what we're talking about specifically here, and I think this is interesting, is we're talking about foundation models that understand geography.
Yeah.
And that's an important distinction, isn't it?
Correct. So a large language model, which is what most people think of as AIs, if you go under the hood of what an LLM is, it's fundamentally taking a string of text and then trying to forecast the next 20 tokens of text. It's actually doing it by tokens, not text. So each word is given a token. You say, here's these 50 tokens, generate the next 200 tokens. So it's a token generation tool, and the tokens in LLMs are language. Now, in geospatial, you could imagine a thing where the tokens might be part of a graph network. It might be connections. It might be human movement, or it might be, there's various other approaches. But the fundamental thing is you have to train this foundational model on geospatial data with geospatial history, because the LLM gets trained on the web and archive and books. So it's trained on language. So you're going to train a geospatial FM on spatial behaviors.
Right.
Now, when you build these models in LLMs or the GFMs, there's kind of 3 steps to it. There's what's loosely called pre-training, which is preparing all the data that you're going to feed in to the training run. There's the training run, and I'll explain how the GFMs are doing the training run, which creates the foundational model. And then there's what's called post-training, which is where you take the outputs from a foundational model and use it to predict things. So insurance, crime, whatever. So
and this is really cutting edge. You know, we've had, probably a couple of years now of experience in using large language models and how the web goes into training those. In geospatial foundation models, this is really cutting edge. It's new territory.
Correct. And there's some academics in America, I think it's Northeastern Uni. There's a team here in the UK up in Leeds and Liverpool who are sort of working on this, and we're working on it. And so what we're doing is we're lifting out the transformer tech that trains the LLMs and using that tech to create the GFMs typically on a graph. So we'll create a graph which is basically just a way of organizing the world's spatial information. And we'll have all sorts of behaviors that have gone through that graph, and we'll use the transformer tech to create embeddings, which are the key elements of the foundation model. And what we're finding, I'll jump slightly ahead and say what we're finding is the actual training isn't the hard bit.
Right.
We're producing GFMs pretty quickly, pretty successfully. What we're finding is the really tricky bit in geospatial, and it's kind of like Geography 101, we should have known this, is the really difficult bit is choices around scale.
Yep.
And choices around how you represent data within your graph and how you connect things. And we're finding that those decisions, which were problems Stan Openshaw wrestled with, modifiable area unit problem, they come back and bite you really hard in GFMs.
Yeah.
So all of our effort at the moment is actually internal to Geolytix, is we're really thinking hard about the pre-training and what we put on the graph and how do we represent it. And then we're thinking really hard about post-training. So if I explain what the actual bit in the middle does, is you show the fully attributed graph to the transformer tech. It whirs away, does its thing, and it produces what are called embeddings, which is a big, massive tensor of like 500 numbers that represents every edge and node on the graph.
And I guess another way of thinking about embeddings is patterns that the machine can see within all of that data.
Yes. Yeah. So if you remember way back on our first episode, if you watched it, we spoke about the idea of of a feature space, that you can have variables and transforms of variables and interactions of variables, and you quickly get to this infinitely large block of data. And then in a traditional regression model, the analyst goes through and picks the bits. What the LLM transformer tech is doing is it's consuming that whole vast array of feature space. And as you say, is finding patterns that are unexplicable, right? We can't go back and pick out the number and say this represents X. So it's quite a mind shift for a data scientist modeler. I'm used to being able to say, well, this, even if I've done PCA or something, I'm used to be able to say, well, this is largely population, this is largely affluence, this is I can't do that.
Yeah, and that's a key challenge, isn't it?
Yeah.
That explainability point is something that we have to deal with.
Yeah. So the transformer tech produces these embeddings, which you then attribute to for every node and edge on your graph. And then say you're wanting to predict traffic, you will say, well, here's this data set of traffic I know in 20,000 places, feed it the embeddings and say, now predict traffic on these other million places. So I can now use the embeddings to do modeling. Or for us as site researchers, it might be, here's 500 coffee shops, look at the embeddings for those 500 coffee shops. Now tell me if I put a new coffee shop here, use the embeddings on the new place to tell me where it's going to be.
Okay, so in summary then, for the listeners, this is maybe the easiest way to think about it. It's a different way of modeling our data, and it's still, I get from what you're talking, largely in the space of research. When can people expect to see the output or the analysis that comes from a foundation model or geospatial foundation model in what Geolytix does?
This year.
Wow.
Yeah. And again, there are academic papers out there on arXiv where you will see people who've gone through this process, largely the Google research teams, and they're publishing results saying, we can forecast this, we can forecast this. They've been slightly generous to themselves and they've benchmarked themselves against very poor models to say that our model is better. That's not our findings so far. When we compare what our GFM can do to what our traditional models are doing, what we're finding is that they're no better. They're just a lot faster.
Right.
Building them is a lot quicker.
Yeah.
And there's quite how this works into what we do day to day is still slightly to be decided, because it's such a moving feast. Like we've had dozens of these things that are just rubbish.
Yeah.
And we're like, you try and do it and it just produces nonsense.
Yeah. Well, I mean, it is very much an iterative science, isn't it? And understanding that process and recognizing what's good, what's bad, how you make improvements, that's fundamentally how you earn your money. And I would expect your customers trust you to do that in a sensible way moving forward.
Yeah, and there's lots of internal debates within our company as well about how we're actually going to use these things, because we keep coming back to an explicability issue, and we keep coming back to a human in the loop issue. And one of our customers said, why would I use AI when I can use real intelligence? If the AI is no better than an expert, well, what's it actually adding to the process?
Yeah.
And that's a really important discussion point, particularly within our sphere, where the decisions that are being made are so big, they're millions and millions of pounds. And I think we said in the first one, no one buys a house because an AI tells them to.
No.
And it's the same in real estate. No one builds a £1 billion development or buys a 10 million plot of land because the AI told them to. There's always humans in it.
Now, I think these have been fascinating insights into your approach, basically. And I see, as a result of, these discussions we've had over the series of podcasts, actually there's a narrative here that you're using ranges of different tools, ranges of different data sets to solve problems. And AI is just another set of tools and another approach to.
Correct. I built a location planning neural net model 20 years ago.
Yeah.
Now that was back in the very early days of neural nets, and again they were rubbish. We just couldn't get them to work, so we said, "Oh, let's park that one, and we'll go and build gravity models, and we'll worry about these things later."
Yeah.
But now, because of the massive compute and the breakthrough from Google in the transformer approach, which kind of revolutionized the speed and utility of them, and a lot of it is compute, right? You hear stories of like. I think the latest Mythos, the training run was something like 3 months or something. Insane. Used more energy than a whole city. And you simply couldn't do that.
No. And that's a key point. I think we often forget about that. At the end of that training run, you have the model. And then, the energy has been, largely used in training. Actually then deploying the model, that's relatively easy.
Yep, absolutely. And I again, don't take any share tips from me. I actually think what's going to happen is these massive training runs, I think they're probably getting close to the limit of what they can do. And all the exciting stuff, I think, is going to happen in pre and post training.
Yep.
It's how you use them, and they don't need the compute. So all of these people spending trillions of dollars building data centers, I think they might find, it's like, do you remember 10 years ago, everyone built fiber networks and they just went dark because no one needed them? I worry that something like that might happen.
So here, Blair.
Yeah.
Sell your NVIDIA shares now.
Sell NVIDIA. Buy Google, I think, at the app layer. And we're not even sure that what I've just described, the graph neural net with the embeddings, we're not even sure that's the right way of doing it.
Absolutely not. Yeah. And I think that's interesting, in the history of this, and I'm sure we'll kind of discuss this in the next step in our conversation. We're very focused on deep learning, large language models, but it wasn't that long ago AI meant expert systems, and expert systems was a valid approach that may well come back again. We don't know. It's very difficult to foretell the future.
I was talking to someone who works in legal tech, and legal tech is because its language is being really shaken up by them, and they were saying, look, we had expert systems 20 years ago to draft contracts. It was just a whole series of if then else's, but maybe we come back to that.
No.
So but watch this space. We have GFMs up and running. They're not very good yet, but they'll get better. And hopefully, if people want to have a play with one of ours, just get in touch.
Well, fantastic. Watch this space.
Yeah.
Very good.